Imagine a giant fire. Not just any fire, but one hotter than the surface of the sun. This inferno rages within the heart of a rocket engine. It's the power that allows us to leave our planet and explore the cosmos. But this power comes at a cost: unimaginable heat, thousands of degrees Fahrenheit, enough to melt any known material. This is the challenge of rocket engine design. We must harness the fire without being consumed by it. How do we achieve this? Through ingenious engineering and a deep understanding of physics. We'll journey into the heart of this fiery maelstrom. We'll uncover the secrets of how rocket engines survive. This is a story of human ingenuity. It's a testament to our relentless pursuit of the stars. Fasten your seatbelts. Our exploration is about to begin. The combustion chamber is where the magic happens. Here, fuel and oxidizer mix and ignite. This creates thrust, propelling the rocket skyward. But the temperatures generated are staggering. How do we prevent the engine from melting from within? One method is regenerative cooling. Imagine a network of tubes lining the combustion chamber walls. Fuel flows through these tubes before combustion. This preheats the fuel while simultaneously cooling the engine. It's like giving the engine a cold drink while using the waste heat to cook your food. Another technique is film cooling. Here, a thin layer of cool gas is injected along the chamber walls. This acts as a protective barrier, insulating the metal from the extreme heat. Imagine a firefighter spraying water on a burning building to create a temporary shield. Ablative cooling takes a different approach. A layer of material is designed to slowly erode away, carrying heat with it. This sacrificial layer protects the underlying structure. Think of it like an ice cube melting in a hot drink, absorbing heat in the process. Finally, we have radiative cooling. Some heat is radiated away into space as infrared radiation. It's like the warmth you feel from a bonfire, but on a much grander scale. These methods, often used in combination, create a delicate balance. They allow us to harness the fury of combustion without succumbing to its destructive power. The nozzle is the rocket engine's exhaust port. It's responsible for channeling the hot gases, generating thrust, but if the combustion chamber is an inferno, the nozzle is where the inferno focuses. Here, regenerative cooling plays a crucial role again. Fuel flows through channels within the nozzle walls, keeping temperatures manageable. It's like giving the nozzle a constant internal shower of cool fuel. Ablative materials also come into play. These materials line the nozzle throat, the narrowest and hottest part. They slowly erode, sacrificing themselves to protect the nozzle structure. Think of it as a heat shield, gradually vaporizing to protect a spacecraft during atmospheric re-entry. High-temperature materials are essential for nozzle construction. Superalloys, ceramics, and refractory metals can withstand the extreme conditions. Imagine forging a sword in the heart of a volcano. These materials are born from intense heat. Thermal barrier coatings provide an extra layer of protection. These coatings, often made of ceramics, act as insulators, reducing heat transfer to the underlying metal. Think of it like a thermos, keeping your coffee hot by minimizing heat loss. The nozzle is a testament to precision engineering. It's a delicate dance between harnessing immense power and ensuring structural integrity. Rocket engines wouldn't exist without extraordinary materials. These aren't your everyday metals. These are alloys, ceramics, and refractory metals, each with unique properties that allow them to laugh in the face of extreme heat. Superalloys are nickel-based alloys that can withstand incredible temperatures and pressures. They're like the superheroes of the materials world, possessing extraordinary strength and resilience. Ceramics are another vital component. They're known for their heat resistance and ability to act as thermal barriers. Imagine the tiles that protect the space shuttle during re-entry. That's the power of ceramics. Refractory metals like tungsten and molybdenum have extremely high melting points. They're used in the hottest sections of the engine where other materials would simply vaporize. Think of them as the mythical metals of the gods, forged in the heart of stars. These materials are the unsung heroes of space exploration. They are the foundation upon which our dreams of reaching the stars are built. Section 5. The Architect's Eye, Designing for Extreme Heat. Designing a rocket engine is like building a house in the middle of a volcano. Every aspect, from material choice to geometry, must be carefully considered to manage the extreme heat. Heat transfer is a primary concern. Engineers use computer simulations and sophisticated models to predict heat flow within the engine. They design cooling channels, film cooling systems, and ablative layers to dissipate heat effectively. It's like designing a complex plumbing system to keep a nuclear reactor from overheating. Thermal stress is another major challenge. Rapid heating and cooling can cause materials to expand and contract, leading to stress and potential failure. Engineers carefully select materials with compatible thermal expansion coefficients and design components to minimize stress concentrations. Think of it like designing a bridge to withstand the constant expansion and contraction caused by temperature changes. Material selection is paramount. Engineers consider each material's melting point, thermal conductivity, strength, and resistance to oxidation and erosion. It's like choosing the right tools for a delicate surgery. Each material has its strengths and weaknesses. Designing for extreme heat is a constant battle against the forces of nature. It requires a deep understanding of physics, material science, and engineering ingenuity. Section 6. Beyond Earth, Future Challenges and Innovations. As we venture further into space, the challenges of rocket engine cooling will only intensify. Longer missions, more powerful engines, and new propellants will push the limits of current technology. Future engines may utilize advanced cooling techniques such as transpiration cooling, where a porous material allows coolant to seep through, creating a protective film. Imagine a sponge constantly oozing water to stay cool in a furnace. Additive manufacturing, or three-dimensional printing, is revolutionizing engine design. It allows for the creation of complex cooling channels and intricate geometries that were previously impossible to manufacture. Think of it like printing a fully functional engine, complete with internal cooling passages, all in one go. New materials such as ceramic matrix composites and high-entropy alloys hold immense promise. These materials offer even greater heat resistance, strength, and durability. Imagine a material so resilient that it can withstand the heat of a supernova. That's the goal. The future of space exploration depends on our ability to overcome the challenges of extreme heat. Through continuous innovation and a relentless pursuit of knowledge, we will continue to push the boundaries of what's possible. Section 7. The Human Spirit, A Story of Ingenuity. The story of rocket engine cooling is ultimately a story of human ingenuity. It's a testament to our ability to overcome seemingly insurmountable challenges. From the early pioneers of rocketry to the engineers pushing the boundaries today, it's a story of collaboration, creativity, and a relentless pursuit of knowledge. Imagine the early days of rocketry, when engines were crude and unreliable. Failures were common, setbacks were frequent, but the dream of reaching the stars fueled the fire of innovation. Through trial and error, through countless hours of research and experimentation, we've learned to tame the inferno. We've developed technologies and materials that seemed like science fiction just a few decades ago. The story of rocket engine cooling is a reminder that we are capable of achieving extraordinary things when we set our minds to it. It's a story that should inspire us to reach for the stars no matter how daunting the challenges may seem. Section 8. A universe of possibilities. The impact of rocket technology. Rocket technology, born from the need to overcome extreme heat, has had a profound impact on our world. It has propelled us beyond the confines of our planet, opening up a universe of possibilities. Satellites, launched into orbit by powerful rockets, have revolutionized communication, navigation, and our understanding of Earth. They connect us globally, provide vital weather data, and allow us to explore the cosmos from afar. Space exploration, made possible by rocketry, has expanded our knowledge of the universe and our place within it. It has inspired generations of scientists, engineers, and dreamers. The technologies developed for rocket engines have found applications in various fields, from aerospace and automotive to energy and medicine. The materials, manufacturing techniques, and heat management solutions have revolutionized industries and improved our lives. The legacy of rocketry extends far beyond the realm of space exploration. It's a testament to the power of human ingenuity and the transformative potential of technology. Section 9. Conclusion. The enduring legacy of rocket science. The roar of a rocket engine is a symphony of power and precision. It's a testament to our ability to harness the forces of nature and bend them to our will. But within that roar lies a hidden story, a story of extreme heat and the ingenious methods we've developed to control it. From regenerative cooling and film cooling to ablative materials and advanced ceramics, we've found ways to protect rocket engines from the inferno they create. We've designed and engineered materials that can withstand temperatures hotter than the surface of the sun. The quest to explore the cosmos has driven us to push the boundaries of science and engineering. It has led to the development of technologies that have transformed our world and inspired generations. As we look to the future, the challenges of rocket engine cooling will continue to evolve. But one thing remains certain. Our thirst for knowledge and our desire to explore the universe will continue to fuel the fire of innovation. The story of rocket engine cooling is a story that is far from over. It's a story that will continue to be written by future generations of scientists, engineers, and dreamers who dare to reach for the stars.